Okay, so we're going to look at the specific latent heat of vaporization of water. So basically, what am I talking about? Well, you know that to add energy to water, and if you keep adding enough energy, it'll turn into steam. So if that steam were allowed to cool down, it would turn back into water, and then it would release energy. So in much the same way that it doesn't take the same amount of energy to melt a kilogram of ice as it does to change the kilogram of ice's temperature by 1 degree. So that's what we call the latent heat. So I want to calculate the specific latent heat of vaporization of water. In other words, that when water condenses from steam back into water, it gives out a certain amount of energy, and I want to calculate that. So I've got a range of numbers here that we measured by experiment, and this is an experiment that is on your course. We would have done it, and we will do it when we resume in September. I have a polystyrene cup. I could use a calorimeter instead, but in this example it's a polystyrene cup. The initial mass of the polystyrene cup in water is 84.6 grams. The initial temperature of the water is 11 degrees. The temperature of the steam is 100 degrees, and the final temperature of the water is 30 degrees. The final mass of the polystyrene cup and water is 87.2 grams. So basically you have a little kind of the apparatus that you would have here is, this would be a steam trap. So you'd be piping steam into your calorimeter, and you've got water in here. The steam goes directly into the water, so it will condense immediately. And much the same way that when you add ice to water, it cools it down, when you add steam to water, it warms it up. So if I know how much water I have and how much steam I add, then I can work out all these. I can work out the mass, the specific latent heat of vaporization of water. In other words, how much energy does steam give off when it's changing state from a gas to a liquid? Now, the thing I don't know here at the minute is the mass of the steam. However, if you look at these two figures, I have the mass of the polystyrene cup and water, and I have the final mass of the polystyrene cup and water and steam. Sorry, that should be. Okay, so the mass of the steam is just, well, I end up with 87.2 grams. I started off in my polystyrene cup. So the mass of the steam is 2.6 grams, which is 0.0026 kg. Now, the mass of the polystyrene cup I can disregard. The mass of the polystyrene cup in water is 84.2 grams. So that means that the mass of the water then will just be 83.4 grams, which is 0.0834 kg. Now let's look at the calculation involved here. What happens? Well, remember, energy isn't converted or destroyed, or created or destroyed. It's just changed from one form to another. So the heat given off by the steam when it turns to water, that's the latent heat, plus the heat lost when the steam cools from 100 to 30 should be equal to the heat gained by the water going from 11 degrees to 30 degrees. So on the one hand, the steam loses temperature and the water gains temperature until they're both the same. Now, we're ignoring energy losses to the surrounding here, and the polystyrene cup is a good insulator, so we can ignore that. If there was a calorimeter, we'd have to take that into consideration. So the heat given out by the steam when it turns to water, that's the latent heat of vaporization of water. And I'll just call that L. So just the latent heat of vaporization. So how much steam do I have? Well, the mass of the steam is 0.0026. Plus, now, the heat lost when the steam goes from 100 to 30. Now remember, this is water here now, and the specific heat capacity of water is 4,180. That's a constant. So I have got how much steam. This will all turn to water then, so it'll be 0.0026 multiplied by the specific heat capacity of water multiplied by the temperature difference. And that's the formula that, mass, specific heat capacity of water, and then the change in the temperature. That should be equal to the heat gained by water when it goes from 11 to 30. So how much water do I have? Well, the mass of the water is this. So 0.0834 multiplied by the specific heat capacity of water. That's how much energy it takes to change 1 kilogram of it by 1 degrees. Multiplied by the temperature change, so it goes from 11 to 30, so it gains 19 degrees. So, taking out the calculator here, so this gives me 0.0026 L. I'll just keep the L in red because that's what we're looking for. This next figure, so okay, and this figure, 0.0834 multiplied by 4180 multiplied by 19, that gives me 6,623.628. Now I'm going to take this figure across and subtract. That'll give me 5,862.868. Multiplied by L. So now I just take that number across, take the 0.0026 across, and divide. And you get joules per kilogram per Kelvin. So that is 2.25. Usually the answers are given in scientific notation, so the decimal point is moved once, twice, 3 times, 4 times, 5 times, 6 times. So multiplied by 10 to the power of 6 joules per kilogram. Sorry, it's just per kilogram.